All right, welcome to The Explainer. Today, we are diving deep into digital image processing. It's the incredible science that lets computers see, understand, and even improve our visual world. Everything from the photos on your phone to the most cutting-edge medical scans. This tech is absolutely everywhere. So let's pull back the curtain and really see how it all works.
So, have you ever seen one of those movies where they enhance a super blurry security photo? Come on, you know the scene. The detective leans over the monitor and just says that one word, enhance. And boom, this grainy, totally useless photo suddenly becomes crystal clear and it reveals the one clue they needed. It always feels like total magic, right?
Well, what if I told you that enhance isn't just some magic word they made up for Hollywood? That core idea, taking a messed up image and systematically making it better, that's a real-world science. It's a whole field, and it's called digital image processing. And get this technology isn't just for spies and fictional detectives. No way. It's in your smartphone's camera, it's powering medical diagnostics, and it's an absolutely critical part of how self-driving cars see the world around them. It's happening all around you every single day. So, how does it actually work?
Okay, so before we can get into how a computer can edit an image, we've got to first understand how it sees one in the first place. Because for a computer, vision isn't about having eyes. It's all about numbers. Just numbers.
See, to a computer, a digital image is really just a grid, a giant matrix of numbers. The easiest way to think about it is like a checkerboard. Each one of those little squares is a pixel, and the number inside that square, we call that its intensity, well, that just tells the computer how bright that exact spot should be. That's it. This grid, this function, is the basic blueprint for every single digital picture you have ever looked at.
So how do we get from the real world to that grid of numbers? A camera sensor does it in two key steps. Step one is sampling. Just imagine laying a grid over a real-life scene. That grid decides where to place each pixel. And, the finer that grid is, the more pixels you're going to get. Then there's step two, quantization. This part looks at each of those points we just sampled and gives it a number for its brightness. But, and this is key, it has to choose from a limited menu of values.
And those two steps, they directly create the two most important qualities of any digital image. Sampling, that gives us what's called spatial resolution. It's simple. More pixels means more detail. Just think about the difference between a 4K TV and an old webcam. And quantization, that gives us intensity resolution, or what we usually call color depth. The more levels you have to choose from, the smoother and richer your colors will be. We're talking the difference between an old 8-bit image and the millions of colors you see today.
So how do we actually get all those millions of colors? Well, most screens, including the one you're looking at right now, use what's called the RGB model. Every single pixel is actually made of 3 tiny subpixels, one red, one green, and one blue. And by mixing the brightness of just those 3 lights, literally adding them together, your computer can create a mind-boggling spectrum of over 16 million different colors. That's how this screen can show you such a vibrant, colorful world.
Okay, so now we know how a computer sees an image. It's just a grid of numbers, right? So let's start messing with those numbers. Let's see how we can start manipulating them. This brings us to our next big topic, image enhancement, which is really the art of making an image just look better.
A super simple but really classic example of this is creating an image negative. All you do is invert the brightness value of every single pixel. You turn the blacks to whites, the whites to blacks, and all the grays in between. And just like that, you get a completely different look. I mean, it's a basic enhancement for sure, but it totally changes how we see the image.
So how does that actually happen with the numbers? Well, we use something called a transformation function. The best way to think of this is like the brightness or contrast slider in any photo editing app. You've used those, right? Well, behind the scenes, that slider is just a rule, a function that takes the original pixel's number, does a little math, and spits out a new number. It does that for every pixel, and poof, the whole image changes.
But things get really powerful when we stop looking at pixels one by one. I mean, what if we looked at a pixel and its neighbors? That's exactly what spatial filtering does. It uses this little grid called a kernel or a filter mask, and it slides that grid all across the image. For each position, it looks at the whole neighborhood of pixels to calculate a new value for the one in the center.
And here's a perfect example of what that can do. If we use what's called an averaging filter, where the kernel just takes the average value of all its neighbors, we can smooth out an image. You can see how it reduces some of that random noise. Now, the trade-off is that it also makes the image a little softer, a little blurrier. And that kind of trade-off, that's at the very heart of almost all image processing.
This leads us to something similar, but different. It's a much more objective process. If image enhancement is basically art, then you could say image restoration is pure science. See, here the goal isn't just to make an image look better. The goal is to repair specific, known damage. So this distinction is really the key takeaway here. Enhancement is totally subjective, right? What looks good to you might not look good to me. But restoration, that's objective. We have a mathematical model for what went wrong, say a specific type of motion blur, and we use science to try and reverse it, to get as close as possible back to the original clean image.
And this is the exact model scientists work with. Think of it like a recipe for a bad photo. You start with the perfect original image. Then you add a degradation function. That's the blur from a shaky camera, for example. And then, for good measure, you sprinkle in some random noise. The damaged image we see is the result of that recipe. Restoration filters are designed to figure out that recipe and then, well, reverse it.
And just like a good mechanic has a whole toolbox for different problems, image processing has different filters for different kinds of noise. If you've got salt and pepper noise, those random black and white dots that pop up, a median filter works like a charm. But for more random, fuzzy noise, what's called Gaussian noise, a simple mean filter often does the trick. It's all about choosing the right tool for the job.
All right, so far, we've only been talking about changing pixels, but now we're going to take a huge leap. How does a computer go from just changing pixels to actually understanding what's in the image? How does it find objects? How does it tell the difference between a person and the background?
The answer is a really cool process called image segmentation. The main goal here is to break down the image into its component parts, to group pixels together into regions that actually mean something. By doing this, you're simplifying the image, making it way easier for a computer to analyze.
And one of the main ways to find these segments is to hunt for discontinuities, basically sudden, abrupt changes in brightness. Think about it. The boundary between pretty much any two objects is going to have a change in color or intensity, right? So we can teach a computer to look for those changes, whether they're tiny points, straight lines, or the complex, curved edges of an object.
So here's how it works. First, an algorithm scans the image and detects all the individual pixels that look like they're on an edge. Then, a separate process comes in and plays connect the dots, linking them up into continuous boundaries. The end result is what you see here. The image is partitioned into these meaningful chunks. Now, the computer doesn't know it's looking at cats yet, but it sees distinct shapes against a separate background. And that is the crucial first step towards true recognition.
Okay, so we've gone from simple pixels to enhancing them, all the way to segmentation. Let's wrap this all up by looking at how these incredible concepts come together in technologies that are literally shaping our world as we speak.
Let's start with image compression. Every time you save a JPEG, you're using what's called lossy compression. It's super clever. It permanently throws away little bits of data that your eyes probably won't even notice, and that's what makes the file so small. It's perfect for your vacation photos. But what about a medical X-ray? You can't afford to lose a single detail there. That's where lossless compression, like you find in a PNG file, is absolutely critical. It saves every single bit of the original data, no compromises. And all of this leads to something as futuristic as autonomous vehicles. A self-driving car is constantly using edge detection, along with a smart technique called the Hopf transform, just to find the solid lines of a traffic lane. It uses those boundary representations we talked about to identify cars, pedestrians, cyclists, and then it takes all of that information to calculate a safe path forward. Every single one of those actions, that's digital image processing, live and in real time. I mean, think about that journey. We went from a simple grid of numbers all the way to a machine that can actually navigate a busy street. The power of digital image processing is just incredible. It has completely changed how we interact with and even understand visual information. So it leaves us with one big question. As computers get better and better at seeing, what will they show us next?